special relativity deals with three specific aspects: the length contraction, time dilation, and the mass increase. And we have a problem, first of all, with the length contraction, as they called it, okay? And you'll see something like this on the internet, okay? Length contraction, and you see an equation there, right? Velocity of the object, that's the v there, over velocity of light, the little c. And as v approaches the velocity of light, that v over c squared, right? That becomes 1. 1 minus 1 is 0. And if you multiply 0 times the length of the passenger, right, the person who's traveling, the observer sees nothing, I guess. Well, but we're not concerned about the math here. We're concerned about something else. The fact that they never define what length is. In fact, what they do actually is something else. They define it as distance. And the question is whether they're talking about, distance or distance contraction, length contraction. Are they talking about distance or length? And it looks like they're talking about distance contraction because they're going to unroll the measuring tape and measure something. They call it length, but they're not really measuring the length. They're measuring the distance from one side of the object, in this case, right, from one edge to the other. So they're not measuring really the length of the object. They're measuring the distance traveled by the tip of the tape. And that's where we start already with a problem. Turns out that they're not measuring distance because distance would be simply the separation from beginning to end. That's not what they do. What they're doing, in fact, we can see this with the muon, right? If you look at the explanation he gave you for the muon, and it looks something like this. What you have is that you have distance traveled from the muon from some arbitrary point to where you're going to measure it, right? And then the muon has a long ways to go still until it reaches the Earth. In this case, we're simulating with mountains, okay? So conceptually, it's the same thing. So it doesn't matter if it's a muon decaying from a pion out there in space and coming to Earth, or whether it goes from one mountain to another. We're going to look at the conceptual part here. And we're saying that, the first part of the trip is distance traveled by this object called a muon, the little red ball there, right? And what is in front of it, that light blue arrow, double arrow or double arrowheads there, right? That represents the distance that it has yet to travel until it decays or reaches the Earth, or in this case, reaches the other mountain, okay? And so what's the problem? Well, they can explain this in one of two ways. They either explain it as a time dilation issue or as a length contraction issue. When they talk about the length contraction, what they're doing is shrinking the atmospheric, the atmosphere in that region. They're saying the atmosphere shrinks, and that's how they prove length contraction. And one of the questions there is whether the distance between the two mountains has shrunk. Okay? Do mountains come closer together because a muon travels somewhere between, somewhere in outer space to Earth? Hopefully not, and then that's one issue. But then they also mix it up with the, what I call distance contraction, or with time dilation. They also analyze this in terms of time. And again, it's all irrational, because what they're saying essentially is they can decrease distance, atmospheric distance, or the distance between mountains, simply because a muon travels somewhere between them, okay? And again, we're concerned more right now, not about the actual debate on that issue. We're concerned here about the definitions. We should really call this distance traveled contraction, okay? Because they're talking about segmented, in other words, locations where the muon was all along, from one place to another. And they're going to talk a little bit about the fact that the muon squashing the direction of travel. They're also going to talk about the fact that the distance between mountains and between or the atmospheric environment there shrunk. Okay? So they have all these explanations. They don't all agree, so the jury is still out on what they really mean by length contraction. Okay? But the point here is that what they're talking about really is distance traveled, either by the end of your measuring tape or by the itinerary of the muon itself. You know, you're talking about a movie, and every frame in the movie has a location, right? And so we're talking about distance traveled and not about separation or length contraction. Okay, we're talking about distance traveled contraction. Okay, so we have a problem there, partly because they're using the wrong language, and that's a big problem in mathematics, mathematical physics. But you know, they don't define any of these words. They don't define distance anyway, so it wouldn't matter. They define distance in terms of length, length in terms of distance. So you have a synonym, you have a circular definition, no definition at all. And they don't define time. Here you have one example. Okay, mathematician is an individual who never defines words. Never. Doesn't have a single word, critical word that makes or breaks his theories defined. Hasn't defined any of them. They don't define energy. They don't define mass. They got like 7 definitions for mass. They use them all simultaneously. Distance traveled, whatever, it doesn't matter because they define it in terms of length. You look up length and it's defined in terms of distance. And above all, time. They don't define time. So here you have 2 pillars of special relativity. Time dilation, right? And the speed of light, which is based on distance traveled, right? And they haven't defined distance traveled, or length, or they have, you know, synonyms there, meaning they don't have a definition, and they haven't defined time. And he doesn't define time. He measures time. He's going to measure something he doesn't understand because he hasn't defined it, and he can't make sense of the word time. And that's what we're going to look at today, the fact that, you know, these words remain undefined even to this day after, we've known about time, for 2,500 years at least. The Greeks talked about time. Aristotle talked about time. So you can say at least 2,500 years we've had the word time or the notion of time. And here we are, 2,500 years later, no one has been able to define the word time. So difficult to define time. Okay, that's the problem. And here's the NIST, National Institute of Standards, right? And this is what the head honcho over there says. Einstein reported to have once said that time is what a clock measures. Some say that what we experience as time is really our experience of the phenomenon of entropy, the second law of thermodynamics. Here at NIST, right, National Institute of Standards, right, we don't worry about any of these, philosophical notions of time. They think defining a word is philosophy, ontology, word salad. I don't know what they want to call it. They think it's petty stuff. Don't define that. Well, we don't care. What they do is they measure. For us, time is the interval between 2 events. So they did attempt to define the word time. And they said it's the interval between 2 events. The problem with that is interval is defined as a period of time. So again, we have these circular definitions. These people don't pay attention to definitions. They don't realize they don't have a definition. They think they defined it. And what they're doing is just going around in circles with definitions. And it says for the most precise measurement, well, that's what they do. They measure, right? Of the second, we took the resonant frequencies of atoms. So they're going to measure. They're not going to define. They're just going to measure. And, a mathematical physicist might say, well, we don't do definition. It doesn't concern us. So why did Newton and all these people try to define time? Couldn't. And then they said, well, let's just leave it at that. And here we are 2,500 years later after the Greeks attempted it, and we have no definition of time. In fact, Aristotle defined it as the number of motion, whatever that is, meaning, it was a mathematical calculation. That's what time is, something related to math. in his mind. Here's for no one ever defined distance or length. Mathematical physicists measure length and distance. In math, length is equal to distance. There's synonyms, right? If you look them up, you'll find that length is defined in terms of distance, distance in terms of length. And what a mathematician does, he unrolls the end of the measuring tape to measure either, okay? Or counts tiles, like you see there on the upper right-hand corner there. You know, he's like a mason laying tiles. He counts them. Okay. In math, distance equal to distance traveled, actually, right? That's what it is. The distance of physics is separation between two objects. Distance traveled is a single object that is moving from a starting point, and you're not going to measure the object. You don't care about the qualitative stuff. What you're going to do is you're going to be either counting tiles or stretching the end of your measuring tape, or even worse, you're going to time it. You're going to say, well, how much time did it take? And of course, you pre-establish some units for distance, and you just add them up in terms of time, how many seconds they took or minutes or whatever. Distance traveled is segmented because it's made out of locations, many tiles, many units, etc., whatever. And the distance of physics is made of a single piece. You know, it's separation between two objects. So you can think of it as made of a single piece, whereas the one in math is made of, you know, segments, little pieces, okay? Okay, so here we have a couple of these gurus. One of them is St. Augustine. He came around and says, if no one asks me what is time, right, I know what it is. If I wish to explain it to him who asks, I do not know. So again, he could not define it. But he wrote a whole book about time and God being the God of time or outside of time. And what was he talking about? He had no clue. He said he could not define it. Newton, in his Principia, the Scholium, he says, I do not define time as being well known to all. Yeah, why define it, Newt? I mean, if everybody knows what it is, you don't have to define it. What did Einstein say? Well, he said, it's what a clock measures. Well, what is galloping? You know, what would he answer? Well, it's what a horse does, I guess, right? But a horse does a lot of stuff. He poops, he eats, he has sex, reproduces, sleeps, moves, right? So which one is galloping? So you can't say what a clock measures. You know, you can use a clock as a paperweight. You can throw it out the window and break it. You know, there's many things you can use a clock for. And the question is, you know, what are you measuring? And one possibility is the Heisenberg uncertainty principle. Goes more or less like this. Okay, here you'll see it. Okay, it says there's two versions of it. One is the momentum and position version, which is if we know everything about where a particle is located, the uncertainty of position is small. We know nothing about its momentum. The uncertainty of momentum is large. But the one we're interested here is the second one there. A quantum state that exists for only a short time cannot have a definite energy. So is that what time measures? Is it a measure of energy? And again, this is the problem with not defining words, one, and on the other one is just leaving it so vague, like Einstein did, what a clock measures. We don't know what it measures. Does it measure energy? Measures minutes? What is a clock measuring, you know? Well, Newton concluded if nothing moves in the universe, time would still be flowing. So he had this notion that even if the universe was standing still, frozen, right, there still would be God's clock, I guess, still running. However, he imagined that. What did Einstein say? Well, he says the rate at which time passes depends on your frame of reference, meaning it's a subjective issue, okay, because he's saying that there's no absolute time as Newton imagined it, you know, that there's this universal clock irrespective of what anybody does, you know, so we all measure, that is the standard against we measure our own clocks. And Einstein said, no, it's relative. It depends on where you're at, how far you are, what you see, what you don't see, you know. Depends on a lot of things. So he says time is variable. And what he held constant was the speed of light, because that's what everybody was able to prove, that light travels at a constant speed. And so they said, okay, what changes is everything else. Length changes, distance changes, time changes. Everything, mass changes, right? Everything changes except the speed of light. Okay, so how do they define time after all? Let's ask some of the gurus of mathematical physics. These are well-placed people, a lot of them big names, celebrities that you've heard about sometime in your life, most of them at least. Here it is. And this comes out of the same interview that they had with Kip Thorne, okay? Matt Weiser says, time is something which at a fundamental level we don't understand. Yeah, after 2,500 years, they don't understand it. Newton, of course, thought time was like a river that flowed, and Kip Thorne adds, time is the thing out there that flows, and I go with the flow. So they think it's a flow of something. They use that word flow, and you can say, well, they're being facetious. They're using figures of speech. No. Either there is something called time that flows like a river, or there ain't. It's just that simple. It's black or white. You can't say that in physics you're going to talk about the flow of time and then say, well, I was just kidding. And go to philosophers to find out what I said, what it means. No way. You got to tell me. John Wheeler, time is nature's way to keep everything from happening all at once. That's about the best one they had. And what did Carl Sagan say? It is one of those concepts that is profoundly resistant to simple definition. Simple or complicated, they never define the word time. That's the status quo, okay? They have no definition for time. But they reach all these conclusions based on this undefined term. That's what's very suspicious, right? We don't have a definition for time, but we do have a definition now that we can solidly chew on for what is a mathematical physicist. And here it is, okay? Mathematical physicist, also known as mathematician, okay? Individuals who boast of how smart they are and then base their entire repertoire of irrational theories on the undefined word time. That's what a mathematical physicist is, especially a special relativist, okay? They reach all these irrational conclusions, but they never define the word time, and that's the one they're going to use to make their case. So, we got a problem there. These people don't know what time is, but they talk a lot about time. It's one of the most important words in mathematical physics. Okay, so how do we define it in science? Not that, the word time has no place in science, by the way, okay, or in physics. We do not use the word time because in science and in physics, what we do is explain, and time is a descriptive word, can only describe. It has no power to explain anything. That's why time is not part of physics. Time is not part of science. We do not use time, okay? They might use it in technology. It's got nothing to do with science. Science, we have to explain a mechanism, and time helps us explain absolutely nothing, okay? So here it is. Let's see if I can show this here. This is, again, the NIST said, keeping time at NIST. Time is an interval. What was an interval? The same thing as time. So they had no definition. How do we define it? Well, it's a comparison of two motions. That's what it always was. For example, you take the pendulum, right? Any pendulum. This is just an example. And you take the rotation of the Earth around the sun, revolution, right? And it's called 1 year. And, you're measuring these two motions. You're comparing them. Time requires an observer, memory, okay, a recording device, okay? And here's another version of that. Okay, you have the Earth going around the sun, and you have and you measure the seconds on a clock. Second hand on the clock, that 1 second is equal to 30 kilometers of the Earth going around the sun. So if you have 1 second on the clock, you have 30 kilometers on the Earth. And you're comparing those two motions. That's what time is. Okay, that's what a second is. And again, time, simply comparison of two motions. A comparison of two motions is not a physical object, by the way, because they treat time, they say gravity warps time. No, only if time is a physical object. And you can't say, well, they were just using a figure of speech, an analogy. An analogy for what? Okay, so they've concluded that time passes, and that's the way everybody talks about it. Time passes, time flows. They say Newton's wrong, time doesn't flow. But then they all use that anyways. They say, well, time passes, time flows. That's the way everybody talks. Like if time were a thing that, flows around you, or passes by your eyes or whatever. And they gave direction to time, everybody puts that arrow going upwards for time. So I suppose you got to conclude that time always points north, because I see it in every single graph that I've seen. I haven't seen time in any other direction except north, right? So now space always goes east, and time always goes north. How do we say it in science? Well, time is not an object, so time does not flow. Time does not have direction. It's directionless, okay? So it's irrational to represent time with a single stick or with an arrowhead, because time does not have direction. And people say, well, the direction is forward. Well, forward's not a direction, okay? That's the problem. You can't say it goes in the forward direction. And that's very, very easy to prove. My direction is opposite to your direction. So which one is the forward direction? Which direction does time flowing in? Is it flowing in your direction or is it my direction? And so time doesn't pass because it's not an object. Time cannot be treated as a noun in physics, as a thing. Okay? It's a concept. Concepts don't move. We're done.